So we've covered ideal gas mixtures. We also talked about some general gas mixture calculations, and then we moved into psychrometrics. What is psychrometrics? The study of moist air. So we have dry air, which is nitrogen and oxygen and carbon dioxide and argon and some others. And we have water vapor, and that's just H2O. And they all behave as an ideal gas. So we're going to lump it into a binary mixture of dry air, treat that as one component, and water vapor, a second component. We have three types of airs. Last time I covered it. The hardest probably is this concept of saturated air. It's where the air, I know it's a little bit on the slang side, but it's holding the maximum amount of water. Meaning it has the partial pressure concept, the partial pressure of the water vapor is equal to the saturation pressure at the dry bulb temperature. It's maximum. It can't be any more. It can't be higher. What will happen is you'll have dew forming. Okay, then we had three temperatures. What's the dry bulb temperature is the easiest. The wet bulb, thinking of a sling psychrometer, and that measures the evaporation off of a wet wicked bulb. And so the lower the temperature on the wet bulb, the drier the air in the room. But if you get no evaporation off of that wicked wet bulb, then the maximum temperature of the wet bulb is the actual temperature in the room, the dry bulb. And that'll be when it's 100% saturated air, when it's 100% relative humidity. So the wet bulb is always less than the dry bulb. Then the next one, it's a little tricky, it's the dew point temperature. What? So you take the concept of, in your mind, lowering the temperature of the air in the room until it starts to dew out. And that would be the dew point temperature. So when does that happen? That happens when the partial pressure of the water in the room currently is equal to the saturation pressure at that conceptually lower dew point temperature. All right. Then there's two humidities. One is on the news, the radio. Oh, it's 30% relative humidity today. It's 60% relative humidity today. So we're very familiar with it, and that relative humidity is originally defined in terms of mole fractions, but we use it in terms of partial pressures. So the partial pressure of the water vapor in the room divided by the maximum it could be, which is the saturation pressure at the dry bulb temperature. So that's what the relative humidity is defined as. We often unravel it. So if somebody tells me the temperature of the air in the room and the relative humidity, I can calculate the partial pressure of the water vapor in the room. It's phi times P sat at that dry bulb temperature. And then the hardest humidity, but the ones that the engineers love, is the humidity ratio. What symbol is this? Omega. Omega, Greek letter omega. And it's defined as, anybody remember? What are the SI units? Kilogram of vapor per kilogram of dry air. Hold it, kilogram over kilogram is dimensionless. You're absolutely right. But it's how much is water vapor per how much is dry air. So it's the mass of water vapor per mass of dry air. Those are the units. So it's per kilogram of dry air, how many kilograms of water vapor do I have in the moist air? All right. Sometimes you think of it as the density of the vapor divided by the density of the dry air. That's true. You just divide per unit volume or per 1 cubic meter, and there you go. All right. Makes sense? Now let's solve some problems. A room contains air at 29 degrees C. What is that temperature? One of the three temperatures. Is it dry bulb, wet bulb, dew point? Dry bulb. It's the easy one. Dry bulb. It's at 97 kilopascal. Which pressure? Total room pressure, Partial pressure of the dry air, partial pressure of the water vapor? Total pressure. Then they say the partial pressure of the water vapor is 3.364 kilopascal. Determine, part A, the partial pressure of the dry air. As soon as you solve for that, I'm going to pause and walk around. I want you to solve for the relative humidity, and then go on down the list, then the dew point temperature. All right? So this is part of my active learning strategy. You're more active, and I get to walk around the room. All right, so a lot of you were able to calculate that the total pressure is the sum of the dry air partial pressure plus the water vapor partial pressure. So the partial pressure of the dry air is the total gas pressure minus the vapor pressure, which gives you dry air is equal to 93.64 kPa. Answer for part A. Relative humidity, even though it's a mole fraction of vapor currently divided by the maximum mole fraction possible if it would be saturated air at that dry bulb temperature, we always use the partial pressure, and that maximum partial pressure, if it would be saturated air at the same dry bulb temperature, is the saturation pressure at the dry bulb temperature of 29. So you pick up the 3.364 kilopascal divided by 4.009 kilopascal, and the relative humidity comes in at 83.9%. Dew point temperature, well, we look at our list of the saturation pressures, and so we find where it's equal to 3.364. So it's right there. No interpolation needed. That's why that number was given the 4 significant digits in the original problem statement, so that the temperature of the dew point is 26 degrees C. That means conceptually, if I cooled that air from the original temperature 29 all the way to 26, it would finally become saturated air. If I tried to cool it to 25, water vapor would condense out. All right, and it would stay saturated air, but now it would be saturated air at 25 if I continue to cool it. How about the mass of water vapor in a volume of 1 cubic meter? I say, please remember, it always behaves as an ideal gas. If it always behaves as an ideal gas, I have one of many versions of the ideal gas equation to use. If I'm interested in calculating the mass, then I maybe do this. The pressure of the vapor, that's the partial pressure of the water vapor, the total mixture volume equal to the mass of the vapor, the R bar divided by the molar mass of the vapor times the absolute temperatures. Notice, this temperature is not a partial temperature, it's the total temperature of the mixture. This volume is not a partial volume, it's the total volume of the mixture. But this pressure is the partial pressure to allow me to calculate how much mass of only that vapor is there. So we calculate the mass of the vapor is equal to the partial pressure times the total volume times the molar mass of vapor divided by R bar times T. So we pick up 3.364. I'm going to drop the units in the interest of time and space, but that's kilopascal. Volume, 1 cubic meter. The molar mass, 18.02 kilograms per kilomole. R bar, 8.314 kilopascal meter cube per kilomole Kelvin. And then the temperature is 29 degrees. I add 273. And there you go. We calculate that the mass of the vapor, 0.02414 kilograms of vapor. Not much. All right. The last part, what is the humidity ratio? So they ask for two humidities, We calculated the relative humidity phi, and now the other humidity ratio omega. And so omega is the mass of vapor to the mass of dry air. And since we just conveniently calculated the mass of the vapor, we can calculate the mass of dry air using the same ideal gas equation. And I'm running out of room, so the humidity ratio is 0.02235. You can leave it dimensionless, or you can say kilogram of vapor per kilogram of dry air. I like to emphasize that it's a ratio. One type of kilogram divided by another type of kilogram. But it truly is dimensionless. Any comments, questions? Yes, sir.
You use the pressure for PDA, right? And now find that mass?
Yes, I would use this pressure to find that mass. So the mass of the dry air is equal to the partial pressure of the dry air from part A times the total volume, the molar mass of dry air, which is 28.97 kilograms per kilomole. And then you have the R bar the same and the temperature is the same. Very good. Moist air is at 100 kilopascal, 30 degrees C, and 84% relative humidity. The air is cooled at constant pressure. Determine the relative humidity if the air is cooled to 29. So it starts at 30, it goes to 29. Then in part B, it's cooled to 28. Then it's cooled to 27, then cooled to 26, then cooled to 25. And what they're asking you to calculate is the relative humidity for each of those cases. So it starts at 84%. As I cool it, what is the relative humidity going to do? Stay constant, go up, or go down? The relative humidity. It's going to go up until it hits 100%. It can't be above 100%. If it's 100%, the air is now, quote unquote, saturated. It moves from humid to saturated air. Okay, so let's do this. How do you want to calculate this relative humidity for just cooling at 1 degree? I want you to do it, okay? I'm going to pause. I'm going to let you work on it. Calculate that new relative humidity if I cool it from 30 to 29 degrees C. So let me pick it up here. What is the relative humidity defined as? Mole fraction. The mole fraction of the vapor actual divided by the maximum mole fraction, right? But this is the partial pressure of the vapor actual over the saturation pressure at that dry bulb temperature. So you say to yourself, well, but is the partial pressure of the water vapor equal to the mole fraction of the water vapor times the total gas pressure? Is that also true? Just like the partial pressure of the dry air is the mole fraction of the dry air times the total mixture pressure. That's both of those are true. All three are true. So what happens is the mole fraction of the vapor changing as I just cool it. As I just cool it, the mole fraction of the dry air and the mole fraction of the water vapor stay the same unless I get to the point where it starts to condense. Then things really get tricky because some of the water vapor goes away, it forms a liquid and collects on the bottom. But as long as I'm just cooling it and not condensing it, the proportion of dry air and water vapor stays the same, so that mole fraction of water vapor is unchanged, isn't it? So the total gas pressure always stayed 100 kilopascal. So what stays constant until you start to condense? The partial pressure of the water vapor. So this stays constant. What's changing as I lower the temperature? The saturation pressure goes down, the relative humidity creeps up. It creeps up. So we find that it goes from 84 to I have to calculate, it's going to be 0.84 times 30, so it'll be 4.247 kilopascal. And then at 29, I divide by 4.009. And a number of you made that calculation for part A correctly. And the relative humidity at part A when it's cooled to 29 is 88.9. Yeah, okay, so right, let's put 89%. And then when you cool it to 28, then the phi is equal to 0.84, 4.247, that's what it starts at. But you're normalizing it to 3.783. And so what's the relative humidity for part B? 94.3%. You're getting closer to 100%. And then let's do it for the next one. 0.84, 4.247 divided by 3.568. And what do you get? 99.99%. So guess what? It's saturated. Guess what the dew point temperature is for the original gas mixture? 27 degrees. So if I go to 26 degrees, what is the relative humidity? 100%. Don't let it go above 100. That just means you're condensing some. And then the relative humidity at 25, 100%. True? Okay. When the dew point temperature is 25 degrees C, that's the temperature dew point, 25 degrees C. What percent of the moist air is vapor? And it's a mass fraction I'm looking for. A mass fraction. Well, let me solve this one. It's a little tricky. You're asked to calculate this mass fraction that's vapor. Wouldn't that be the mass that's vapor divided by the mass of vapor plus mass of dry air? So if I inhale so much of this moist air, I'm inhaling so much percentage of water. And we want to calculate it when the dew point temperature is 25 degrees C. Okay, so I look down here, there's 25 degrees C, there's 3.170. So what's the partial pressure of the water vapor in a moist air mixture? 3.170 kilopascal. They don't give me the total moist air mixture pressure. I have to assume it. What value am I going to assume for the total mixture pressure? 1 atmosphere, either 1 bar or 101.3 kilopascal or 1.013 bar. Either one of those. It's going to be close enough. Okay, so that means the partial pressure of the dry air is P minus, we've done that before. So there you go. So now the question is what is this, how do I calculate either the mass or I calculate the mass density? We've done that before, all behaving as an ideal gas. So the mass density, using the ideal gas equation, is going to be the partial pressure of the vapor times the molar mass of the vapor divided by R bar T. Then I do P molar mass of vapor divided by R bar T plus the partial pressure of dry air, molar mass of dry air divided by R bar T. Does that look okay? So I can count, yes or no?
Can we get rid of the R bar T?
Yeah, we're going to get rid of that right now. The R bar T's all cancel. And now it's a lot easier. So we can stick in the 3.170 times the molar mass of vapor, 18.02, divided by 3.170, 18.02. And then I'm going to put 101.3 minus 3.170 times 28.97. And that will give me the mass fraction. If you run that, it'll come in right around 2%. 2%. So you can, moist air can hold quite a bit of water vapor. But this is a bunch of water vapor. So to help put it in the context, you can look up on the internet the dew point temperature of the air that you're breathing in degrees F. I know that this is degrees F here, and we just solved it in 25 degrees C, which is 77 degrees F, 25 degrees C. And we just calculated that the mass fraction of the water vapor in the moist air is right at 2% by mass. That's the mass fraction, 2%. We just made that calculation. And if you were actually in a room that had the dew point temperature that high, it would be above 76 degrees F for the dew point, because it's 77. And you would say it is completely miserable as an occupant of that room. If it dropped in this range, 71 to 75, let's put it right in here to there, not a huge change. It's still near 2%, but it's falling. You would say it's oppressive. If it was 66 to 70, it's still very high. You would say it's getting sticky, but it's the mass fraction of vapor is above 1.3%. Comfortable, now it's 56 to 60. Or if it's less than 55, it's pleasant. Last few days, actually last couple weeks, it's been quite pleasant, hasn't it? Moderate temperatures, low humidities. It will be reflected in the dew point temperature being pretty low and comfortable. And then as it goes up, you can see. But seriously, what is kind of the minimum here from pleasant to miserable? Only from 0.5 to 2%. It's not that much of a range of water vapor. Water vapor affects your sense of comfort strongly. How many people, again, I always use Houston as an example. I go there and man, sometimes I get out of the car after I've been driving, it's air conditioned, it's August, and it hits me like a brick wall. Is it the temperature that hits me? Nope. It's the humidity. You had a comment?
For this question, when you ask for the percent of water, how do you know there's the percent by mass as opposed to the percent by anything else?
I made up the question. So
Let me rephrase. How would I know on a test?
It would be pretty hard. You'd have to either assume to say, look, I'm going to do it on a molar basis and solve the problem, or on a mass basis. You only have two choices, right? So molar or mass. But I was looking for the mass fraction. That would be a poorly worded exam question if it left you in doubt. Anybody else comment or question? All right, I've got about 10 minutes to solve a very hard problem. How about if I give it a shot and you just listen in? This is a hard problem. Okay, we have moist air at 40 degrees C, 100 kilopascal is 75% relative humidity. So atmospheric pressure, 40 degrees C is very hot, but hey, it's 75% relative humidity. It's a lot of humidity. It's contained in a 2.5 cubic meter, and these words are critical, closed rigid tank. All right. The tank contents are now cooled. So it starts at 40 and it's cooled to 35. Calculate the amount of heat transfer in kilojoules needed to cool it to reach the final temperature at 35 degrees C. Then redo the problem to 30 degrees C. So we have a rigid tank, little pressure gauge on it. As I'm cooling it, what do you think that pressure does? Does it stay 100, or does it go up, or does it go down? That's going to make a problem challenging. The pressure is going to go down as well. Now, what about the volume? The volume starts at 2.5 cubic meter. I start to cool it. Does the volume go up, or does the volume go down? You're very good. You didn't let me trick you. It's a rigid tank. The volume stays constant. So the volume's going to stay constant. Now, your experience is the relative humidity is 75%. Constant volume. I start to cool it. Is the relative humidity going to stay the same, go up, or go down? Relative humidity. It's going to go up. Why do you think there's a part A, cool it only to 35 degrees C, and then a part B, cool it all the way to 30 degrees C? What do you think magically is going to happen between 35 and 30 degrees C? For this, you have the dew point temperature in between somewhere. And when you hit it, guess what's going to happen? Some of that water vapor is not going to stay as an ideal gas. It's not going to stay in the gaseous state. What's going to happen to it? It's going to condense. Now, when it does condense, it's going to collect on the bottom of your container. True? Now, do you think the volume occupied by the gas, the moist air, will be significantly reduced by now the presence of the liquid, or will it be insignificant? It'll be so insignificant. I calculated it, and the volume that is occupied by the liquid when it goes to 30 is 0.0008%. I would say as an engineer that's negligible. So don't worry about the volume that's occupied by the liquid. But the first thing we do is we solve the problem when it's easy for part A, and then we throw in the curveball, the hard one, when you condense. What's my general equation for, let me turn this around so you're more familiar with it. This is Q coming into the system during the process one. Professor, it's being cooled. I know it. So it's going to be a negative Q in. But what is my general statement of the conservation of energy? Forget about ideal gas mixtures and moist air and all that. What is it equal to? I like it. Set internal energy. How many students after 2 A's in Thermo 1 and Thermo 2 wouldn't be able to write the first law of thermodynamics for a closed system undergoing a process from initial state 1 to final state 2? They get lost, discombobulated. It's been a couple weeks, Professor. How am I supposed to remember that? No. It's U2 minus U1. True or false? So we can bust it into the mass, that is vapor or water, let's see, water, times U2 minus U1, and the mass, that's dry air, U2 minus U1. This will work for part A as well as part B. And you could say, I'm going to treat it as the vapor, as it always stays ideal gas, and that's going to be for part A. That'll be definitely true. To specific heat, constant volume of the vapor. Maybe I should do this. That V on that C is its constant volume. This V over here is vapor, so it's the mass of the vapor times the specific heat constant volume for steam vapor. All right, times the final temperature, initial temperature, plus the mass of the dry air times the specific constant volume of the dry air times T2 minus T1. That's the Q 1 to 2. I know I'm going to get a negative because the T's are lower. T2 is lower than T1, right? Okay. Do you like this equation? That equation will work perfect for part A. How do I modify that equation when now I got some liquid forming?
The extra energy for the transition across the vapor zone from saturated vapor to saturated.
Conceptually, you can still take it and cool the vapor all the way down to a temperature where the final temperature is 30 degrees C. All of the vapor, all of it down. But then what you have to do is you have to get the mass that actually of the vapor that condenses. It's going to be cooled and then condense. Got it? So even though you still have that sensible cooling of the vapor before it condenses, you still include it. But now I need to get the heat transfer associated with condensing some of that vapor, which is going to be now liquid. And that's going to be what? Right here. What do I put right there? It's not that hard.
Latency.
You got it. So you go U. What does it end up? Saturated, liquid. How did it start? Saturated vapor at the 30 degrees C. And then you have the M C sub V of the dry air times the T2 minus T1. Again, these for this one, for part B, this is 30 degrees C. True? This is 30 degrees C. Okay. Where before this was only 35 degrees C and the 35 degrees C. So you don't have any condensation as long as you don't go below 35. But when you get down to 30, you have some condensation. Now, this equation should make sense. Professor, how come we don't put an H in here? HF and an HG. Because it's not needed. It's constant volume. If you had constant pressure, you would have to use CPs, and you do an HFG. HG. Well, this is a minus UFG. It's a negative amount. Okay. Does that make sense? All right. Looks like I'm out of time. So maybe I'll solve this problem next time. Thank you.